Yeah, happy to be here to talk about a special technique in MegaETH, which we call node specialization. So a bit about me. My name is Lei, and I'm a co-founder and CTO of MegaETH. Yeah, so first, some background on MegaETH. So we see a very special opportunity to bring the Web2 level of performance to the crypto world. And we call this vision a real-time blockchain. In particular, we define it with 3 criteria. First is that the blockchain should be able to process transactions in real time as they arrive at the chain. And we specify that by a 1 millisecond or lower block time. Second, the blockchain should be able to execute and commit the states and also propagate the states within a 1 millisecond latency. So in other words, from a transaction getting to the sequencer to the state being computed and being ready for nodes to fetch, the latency should be less than 1 millisecond. And third, the blockchain should be able to sustain this level of real-time responsiveness even under heavy load. And that is a throughput of more than 100K transactions per second. So a bit about our founding team. The founding team consists of computer science PhDs from Stanford and MIT, and also business professionals from Consensus. All right, so in the next 10 minutes, my goal is to help you understand what is node specialization as a technique, why we think it's inevitable to implement it if you want to build a real-time blockchain, and also how MegaETH is pushing this idea to the extreme to build the very first real-time blockchain. All right, so first, what is node specialization? So the idea of node specialization is actually quite simple. It's about taking the tasks in a blockchain and assigning them to different cohorts of nodes. And then by doing so, we're able to optimize each cohort of the nodes corresponding to the particular task they are assigned to. And this is a comparison to a traditional blockchain model where every node will be able to, where every node will be responsible for every task in the blockchain. So to make it more clear, we can look at kind of an abstract architecture of a blockchain, and we can see why node specialization is so important here. The key reason is that blockchains are inherently heterogeneous systems. So what I mean here is that if you look at the flow of transactions in a blockchain, first you have transactions coming to the blockchain, and the chain has to sequence those blocks and execute those transactions to get to blocks and the final states after the transactions has happened. And ultimately you want to serve some users or some applications. So you have to disseminate the latest state to the users, and we call this process dissemination. And of course, the users wants to get the proof, get the kind of the confidence that the state they're accessing is correct. So you have to use validator to validate the latest states and generate proofs for the end users. And of course, you also want to make sure that transactions, once confirmed, will not revert. And in other words, you need a process of finalization for these transactions. And the key takeaway I want to get to is that these tasks have very different requirements in terms of the performance of the nodes that are assigned to these tasks and also the decentralization level of these nodes. So here I'm showing a trade-off between the node level performance and the decentralization. So for the on the horizontal axis, I'm displaying the kind of the node hardware requirement. You can think of it as how powerful a node is, the beefiness, and on the y-axis, it's how much decentralization such kind of nodes can get to. So the green line is an inherent trade-off between these two parameters. Because if you want really powerful nodes, you cannot really hope for many users to be able to maintain and set up these nodes. Because nobody wants to have a server with 1 terabyte of RAM humming along in their living rooms or in their data centers. On the other hand, if you want really good decentralization, you have to really build very lightweight nodes, like Raspberry Pis, which people are happily kind of plugging into their routers at their homes, right? So this is an inherent trade-off. You can get very powerful, but not too much decentralization, or vice versa. So if we look at these tasks, right, for sequencing and execution, I think as Kyone mentioned, it's super IO intensive, it's super CPU intensive sometimes. So you do need really powerful nodes. And for validation, because it's kind of the bedrock of blockchain security, right? It's because so many pairs of eyes, so many validators are kind of monitoring what the sequencer is doing so that we guarantee that the sequencer is correct. So you do need a high level of decentralization. And in a traditional architecture, because when there's no node specialization, every node will have to work on every task. And in particular, there's only one type of node, one configuration in the network. So you are forcing all the tasks to converge onto one point on this trade-off spectrum. So for example, here I can use a very lightweight node to run all of these tasks. And here, it's like the trade-off that Ethereum is taking. Ethereum says that I want home staking, I want people to be able to just set up second-hand desktops to run Ethereum nodes. So it's good level of decentralization, but there's not enough power in those nodes. And that's why Ethereum nodes cannot really execute transactions so fast. And that's why you have a low throughput. Yes, so yeah, you can see that validation and finalization, they are super happy because they get their level of decentralization. But yeah, sequencing is not being served really well. On the other hand, you can also try to use very chubby servers to serve as your nodes. So in this case, sequencing will be really happy because it gets this level of power, but the chain will not have too much decentralization. And this is kind of the other end of this trade-off spectrum for traditional blockchains. And so you will see the key takeaway here is that no one is served well simultaneously. Not everyone is served well simultaneously, right? So what we can do with node specialization is to define and set up different cohorts of nodes for each task. So we will have very chubby nodes dedicated to one task, which is sequencing and execution. And on the other hand, we have super lightweight nodes to do validation, and we have other types of nodes in the middle to handle these tasks. And here the key takeaway is that you will see everyone's super happy because there's one tailor-made type of nodes serving their task. So let me quickly summarize. It's because that blockchains are inherently heterogeneous. There are different tasks with different requirements on the performance versus decentralization trade-off that you want different kinds of nodes. And if you do not specialize the nodes, then you are forcing every task to converge on the same kind of hardware specification and decentralization level. So everyone has to take a compromise. While if you specialize the nodes, then everyone will be served much better, even optimally, because you can just tailor-make your node for each particular task. And if we put it back to MegaETH, we'll have a few sequencers, actually one at any given point in time, with 100 plus CPU cores, 1 to 4 terabytes of memory, the latest generation SSDs, and really good hardware to run sequencing. And on the other hand, the provers will be really lightweight, 1 CPU core, half a gigabyte of memory, and literally no storage needed to run validation. And in the middle, we use Ethereum and EigenDA for finalization because we think it's the best combination of security and performance. And we will have relatively lightweight full nodes on par with current Ethereum nodes to kind of replicate the state of the current blockchain and disseminate the results to our users. So yeah, to quickly summarize, we have maximally powerful sequencers to execute the transactions, maximally lightweight provers to validate the transactions, and get to a really decent level of decentralization. Very accessible, home operable full nodes for you to kind of get up to date with the blockchain state, and with inherent security from Ethereum and EigenDA. So before I end, there is a quick twist of the plot. I've been talking about node specialization all the time, but actually it's just the first step towards a real-time blockchain. So in other words, I want to say that node specialization is not kind of sufficient for us to arrive at a really high-performance real-time blockchain. It's a good step towards that goal, but it's not sufficient. On the other hand, it is a really necessary step because, again, it allows us to tailor-make a particular type of hardware and software combo for each task in the blockchain so that we can be really optimal in terms of the hardware and software executing each task. And in particular, many of our optimizations on the node level are not really you cannot really replicate these optimizations if you do not do node specialization. So I want to make probably one example, which is the parallelization algorithm that I mentioned, that Keone mentioned. So I guess different from many other parallel EVM layer ones, we do not use optimistic concurrency control, which I think Aptos, Monad, and many other players in the field are working on. And the key reason here is a failure called a cascading upward, in the sense that if it happens to be that in your block, the transactions have so much interdependency that to the level that it will even be slower for you to attempt to parallelize them. Because the thing is that if you have so much interdependency in your block, you can literally not parallelize them physically, right? It's from a mathematical standpoint. However, if you attempt to do that, this attempt will actually cost you more time and resource consumption than just kind of executing them sequentially from the very beginning. And by not using what we call a deterministic parallelization algorithm, we can actually avoid that problem and use a class of algorithms called non-deterministic parallelization algorithms, which will be provably free from this kind of cascading upward problems. And for example, this is a key difference between us and other blockchains working on parallelization, and it's only enabled by node specialization. All right, so I'll conclude here and take questions, and I would invite you to look at our research content on our website and also attend other events at ETHDC. Thank you.
Thank you. Quick question, similar to Monad, like what kind of new projects are building on top of MegaETH right now, except for fully on-chain DEX Keone just mentioned?
Yeah, so good question. We have very interesting consumer apps, which I cannot tell about too much, but we have a really good cohort of builders, which we call Mega Mafia. Some of you might have been to our hacker house. It's just kind of 3 blocks down the road, and I would really invite you to go and talk to the builders. Yeah.
Cool, and also because we have different types of node requirements, are we using different methods to curate them?
Different methods to curate them?
Like bootstrap, for example, validators, sequencers, because the requirements are different. Are we different methods?
Of course. So, yes, good point. For sequencers, we envision them to be run by really professional providers. We will eventually decentralize the sequencers, but not by kind of putting a consensus algorithm in a critical path like layer 1s do, but instead rotate the active sequencers. But yeah, we envision only kind of professional hosts to kind of operate them. And on the other hand, provers are really lightweight. We really put a lot of thoughts into kind of making provers as lightweight as possible. So we, as I mentioned, the hardware requirement will be 1 CPU core, 5 GB of memory. And it's kind of even more lightweight than a $30 Raspberry Pi. So we kind of think that even current Ethereum home stakers will be able to do them. And actually the hardware requirement is actually lower than Ethereum nodes.
Got it. Yeah, and also because we are real-time blockchain, the latency is super low. So I guess the sequencing method we use is first come, first serve?
Yes, so exactly. We do currently, at least at launch, we do not plan to put any kind of auction in the critical path for sequencing. Yeah.
Cool. Yeah. Any questions from the audience? Okay, come on.
Just in my understanding that compared to the monad can be understood as layer 1, so it is cannot ask like some high-end hardware to run it, and MegaETH is a layer 2, so kind of can improve the hardware requirements and just let everyone or live client can do the validation. It kind of like increase the TBS. So do I understand correct?
Yes, correct. So the key here, but as I mentioned, right? So I think the trick you mentioned is basically no specialization, right? Because the key insight here is that you don't need everyone to be fast in a layer 2. You only need the sequencers to be fast in a layer 2 or any of the blockchains, right? And that's one contributing fact. But as I mentioned here, so MegaETH is definitely not just kind of turning up your hardware to 11, right? No specialization really just gives you the freedom to kind of spec your hardware as much as you want and also run those optimizations however you like. So for example, all these optimizations, they are only kind of practical when you have specialized nodes. Yeah.
Great. Makes sense. Another quick question is, I read the MegaETH stack before and it claims to be the 1 million TPS, some kind of like a very high number of TPS. But my question is it really necessary to achieve so high TPS? Because sometimes you just need to batch it or provide some proof of a series of transactions. So what's the idea about it?
Well, you mentioned to batch transactions.
Yes, exactly. Maybe just give me some, just maybe batch several transactions like to the state to verify on layer 1, some kind of like this.
Yeah, correct. But someone has to execute these batch of transactions, right? So layer 1 will have the job of kind of really securely verifying the proof of this batch, but the job of layer 2 or the job of a blockchain that an end user actually interacts with will be to actually run through every individual transaction in this batch. So you cannot kind of escape that from that problem. So the high TPS is really needed. Yes, Ethereum may not need 100K TPS, but some will have to provide, because otherwise, who is going to run this batch of transactions? And to kind of continue on the question, we really envision kind of an abundance of computation on chain, and we don't think it's there now, because when you write smart contract, you still worry about gas gulfing, you still want to minimize the gas cost. But you do not do that when you do JavaScript programming, right? A Chrome tab is 1 gigabyte plus my memory now on my MacBook. It's crazy, but we want that craziness to happen on blockchain, so that it kind of releases the productivity from the developers, right? It's like assembly language programming back in the 80s versus JavaScript, Python programming. To the eyes of an assembly programmer, JavaScript is insanely inefficient, but it's insanely powerful and insanely productive to program in that language, and we want that happen we want that to happen on blockchain. Yeah.
Awesome, totally makes sense. That's all my questions.
Again, thank you so much for the presentation. Can you go back a few slides about finalization? The place where you mentioned INDA. Just very curious if I mean we understand like Ethereum blocks takes 12 seconds. Do you think that the speed of INDA is something that is suitable, or are you probably looking for a faster alternative?
Yes, so the key here is to realize that for DAU, it's not sitting on a critical path.
Right.
Yes, so what matters here is throughput in terms of how many bytes INDA or any DA can kind of provide data availability for per second versus how long it takes for EigenDA to respond to a particular request. So in that sense, EigenDA is totally, EigenDA is kind of the leading product in both fronts, both throughput and latency, but yeah, and the throughput is totally suitable for us.
Got it, thank you so much.
So I have a question around the real-time proving part.
Okay.
So how is that achieved? Because right now we know we have ZK proof and OP proof. I'm not so sure about the OP proof, but in terms of like ZK proving, it actually requires a lot of like computation power, and it's not as efficient as right now. So
yeah, very good question. So that's why we are not doing ZK proof at launch. So probably I should have mentioned it. So here for maximally lightweight, I do mean OP provers or OP validators or just fault proof generators. And for OP proof, it's not on a critical path. The way it works is like we assume the sequencer is correct until such a fault proof is raised post hoc, right? So yeah, that's how it works.
thank you.
How are you thinking about sequencer rotation?
Sequencer rotation?
Yeah.
Sequencer rotation as in the mechanism to implement it, or the comparison to, say, a consensus protocol that sits in the critical path?
The method to implement it.
There are many. I think one feasible way is to do an auction, for example, for sequencing rights. And that would be kind of the incentive level, and we are still kind of working on it. On the kind of the technical side, how to actually implement sequencing rotations from kind of a code level, it will be, you will need a consensus algorithm. It can be a layer 1, or we can run our own consensus algorithm, which I don't think is really needed. So you need kind of the auction to happen transparently on a chain with consensus algorithm, with kind of good trust, inherent trust. And then kind of the auction result will be deterministic based on the bits that happen on this chain, and everyone will just look at the chain and see that, hey, next hour I should go to that sequencer, and I'll just go there.
Thanks.